Okay, let's get started. Thank you for braving the weather this morning and making it in for class. We're going to spend the first few minutes today just talking a little bit about the assignments, and then we'll get back to the lecture material. Okay, fingers crossed. Who has PyroSim installed and running? Okay, good. Hands up if you are still struggling with a PyroSim installation. One. Okay, we're down to one. That's good. Come and see me after class and we'll talk about it. I had a look on Blackboard this morning and it seems pretty much everybody submitted their first assignment. So I think you're over the biggest hurdle in this class, which is getting PyroSim installed. All good with that? Okay, so let's talk this morning about the rest of the assignments. So just as a reminder, I've sort of restructured the schedule here for you a little bit, hopefully to make things a little bit clearer. So remember that the undergraduates, you're going to be submitting one assignment a week, and the grad students are going to be working on 2 assignments a week. So for the grad students, you should have completed assignments 1 and 2, and you can move on today to assignments 3 and 4. Okay, so let's talk about assignment 2 for a moment. As you've already realized, there are the assignments in Reddit, and then there are the weekly assignments that you're doing. Some of the assignments on Reddit are rather short, so I sort of bunched them together. So some weeks you'll be doing multiple Reddit assignments, and other weeks it'll be just one Reddit assignment. So assignment 2 combines 2 assignments from Reddit, which is the assignment where you're going to be creating objects, and the next assignment where you're going to be creating joints. Next week, assignment 3 is a longer one, and it's about sensors. So that one, assignment 3, is just the sensors project on Reddit. So again, this week you're going to be tackling objects and joints. So let's skip to assignment, the objects assignment here. Oh, I forgot to mention one other thing. For those of you that have managed to install PyroSim on Windows, we just figured this out in the lab this week, that the time period in Windows is much shorter than it is in Linux or Mac in PyroSim. So if you're on a Windows machine and you run the first assignment, usually if you're on a Mac or a Linux machine, the empty simulation pops up for about 5 seconds and then closes. That's what you should see. In the Windows, if you do it on Windows, it opens for like half a second and closes. Has anybody seen that in Windows yet? Okay. So that's fine. It doesn't matter to us how long or how short your simulation runs for now. It's going to matter later when you want to get your robot to do something. Obviously, we need to allow the simulation to run long enough for your robot to do something. So for those of you that have an overly short PyroSim simulation running, you can extend the length at which an evaluation runs for by simply typing in an argument when you create the simulation. So the default for a simulation is 100 time steps, which on Mac and Linux seems to be about 5 seconds of real time. 100 time steps in Windows seems to be much shorter, so you can lengthen your simulation by lengthening the evaluation period. So in all the assignments to come, it doesn't really matter to us how long or how short your simulation runs for, just that your simulation runs long enough to demonstrate the behavior that we ask for in the assignment. So if it opens up and your robot doesn't have time to do whatever it's supposed to do, go to the first line where you construct your simulation and lengthen the evaluation time. Make sense? Pretty straightforward? Okay. Okay, that's all I wanted to say about that. So just a little bit about objects and joints now. So again, through the assignments now, you're going to start with your empty simulation, and we're going to gradually add all the necessary components you need for a robot. And we're going to start with the robot's body. Remember, we talked about René Descartes last time, body and brain. So we're going to start in assignment 2 with the body. You're going to be creating a number of 3-dimensional objects that make up your robot. And we're going to be making a minimal robot, which is simply made up of 2 objects, these 2 cylinders to start with. One of the things I want you to get comfortable with is the coordinate system in our virtual environment, in PyroSim. So let's see if I can do this with my back to the board. To the let's do it this way. This will make it easier. So negative x is to the left. Positive x is to the right. Negative z is below the ground. Positive z is up into the air. Negative y is outwards towards the viewer. And positive y values are into the screen. So we're going to start to do a lot of things with positions and orientations, and I'm going to refer a lot to x, y, and z. So x is horizontal, y is into and out of the screen, and z is up and down. Okay, so obviously at the beginning of this assignment, when you create an object, like in step 13 here at the top, we need to give our object a position. So where's the center of that object? And we need to tell PyroSim something about the geometry of this object. So if we're creating a cylinder, we need a length and a radius. And then a little bit later, when you're creating your second object, you're going to also be playing around with three additional arguments, R1, R2, and R3. These correspond to x, y, and z, and they refer to the three-dimensional rotation of the object in space. So this can be a little bit non-intuitive if you haven't seen this before. So when you create a default object and you don't specify R1, R2, and R3, the cylinder starts in a vertical position. You'll notice that the second cylinder, which we're going to paint red just so you can tell them apart, is not going to be vertical, but it's pointing in what direction? It's pointing, we need to be more specific, right? It's perpendicular. Use the coordinate system here. What is the orientation of this red cylinder? Sorry? Parallel to the xy plane. That's correct, right? So it's embedded along this vector, so it's embedded in the xy plane.
So z equals 0?
Sorry?
Z
equals 0, that's one way to do it. So the way that this is done in PyroSim is when you want to specify the three-dimensional orientation of an object, or how it's rotated in three-dimensional space, you're going to imagine that cylinder, that its long axis is lying along a three-dimensional vector in space. So if you want your cylinder to be something other than vertical, you need to tell PyroSim what is that three-dimensional vector along which the long axis of that cylinder should lie. So you can see that when we first create the second cylinder, we don't set R1, R2, and R3, so it starts vertically. Now we've set R1, R2, and R3. We've changed the initial 3D rotation of the object. What is the 3D vector, given our coordinate system here, that defines this cylinder?
Rotated 90 degrees about the x-axis.
Absolutely. So there's lots of ways to specify orientation in three-dimensional space. So we know that it usually starts vertically, so we could specify a rotation angle. Those are known as Euler angles. We're not doing it that way. We're doing it by saying, here's a 3D vector in space, and in 3D space, and we want the cylinder to start by lying along that vector. What is that 3D vector? Someone just said it. 0, 1, 0, right? So I'm going to skip back and forth here to the actual coordinates. So you can see here at step 33, you're setting R1, which is the first rotational axis, which is really x. Maybe we should rename these x, y, and z. R1 is 0, R2 is 1, and R3 is 0. So if we go back here, right, x is 0, z is 0, and the middle coordinate, which is y, is 1, right? So in essence, we're actually saying x equals 0, y equals 1, z equals 0. It's that vector which starts here and points into the screen. Take that 3D vector and lie the cylinder along it. Make sense? So as you move forward and you start to build your own robot, and you decide that you want your cylinder to start like this, you have to figure out what is that 3D vector. Tell PyroSim what that 3D vector is, so your cylinder lies along it. but you also need to set the position, right? So now we're setting a total of 8, we're sending 8 parameters to describe a cylinder. The first 3, x, y, and z, is where's that object in 3-dimensional space. R1, R2, and R3 specify how you want it to be rotated in space. And what are the last 2 parameters?
Yeah.
Sorry?
Yeah.
Length and radius, right? So we've got the position of the object in space, the orientation of the object, and parameters describing the geometry of the object, which in the case of cylinders are radii and lengths. Later you can create boxes and spheres and so on. You specify the geometry of those. There's also, of course, RGB. You can paint the object whatever color you want. Make sense? So you're going to be doing a lot of manipulations in 3-dimensional space. So the objects assignment is a good place to take some time and get comfortable with the coordinate system and how to specify, in this case, 3-dimensional orientations of the object. Right? You can test yourself by, instead of putting the object to lie along the vector that points into and out of the screen, maybe you take the red cylinder and you get it to lie horizontally. What would be R1 and R2 and R3 in that case? So we want to take our vector, which if we don't specify R1 and R2 and R3 starts vertically, and we want it, I'm not going to pour out my coffee here, we want it to lie horizontally. How would we do that?
1, 0, 0.
1, 0, 0, right? So you know that, put that in, run your code, and that's what you should see, right? So I also want you to get into the habit as you work through here of making predictions about what your robot is going to look like or what your robot is going to do when you make a change to your code. One of the nice things about working with physics engines is you can kind of see everything, right? So this is sort of proactive debugging, right? You'll know that you have a good intuition if you set R1, R2, and R3 to be 1, 0, 0 and you start it up, and if your cylinder does not lie horizontally, you're missing something, right? So feel free to play around with the simulation to build up an intuition for specifying 3D coordinates for your objects. Okay, so in the second part of assignment 2, you're going to be working with joints. And joints are going to, like your knee joint or your elbow joint, allow you to connect objects together. And for our purposes for the moment, joints are just going to allow objects to rotate relative to one another. So joints, unlike objects, are a little bit tricky because they're not drawn by the simulator. They're invisible. So the only way you can infer whether you've got the joint specified correctly is by observing how the 2 objects rotate relative to one another. So again, this assignment can be tricky for some people if you don't have a good intuition for the 3D coordinate system in PyroSim. So let's just talk a little bit about joints first to give you a bit of an intuition about this. This is the snapshot here where we put the red cylinder up here and then it just falls because the 2 objects aren't attached yet. You're then going to attach these 2 objects together with a joint, and your robot is going to fall forward like you see in panel B here because it's attached at the point where the cylinders connect. What is that point? What is the XYZ of the point at which the cylinders touch one another?
0, 0, 1.
Close. I'm sorry, I think I got ahead of myself here. Let's go back a little bit to, in the assignment on objects, if I can find it here, you're going to be sketching an engineering drawing so you can keep track of all of these positions and orientations. So an engineering drawing is a drawing of some 3-dimensional object or a collection of objects. The normal way to do this is take a sheet of paper, break it into 4 panels. You're going to have a back view, a side view, and a top view of your robot. And I just pasted a perspective view here for you so you can see what's going on. I highly suggest that when you make your own engineering drawing in this assignment that you do it in pen and pencil. You do it in paper and pencil, because you're going to be adding and removing and changing a lot of things to this drawing over the next few assignments. If you want to do your engineering drawing on the computer, that's fine too. Just make sure that you can easily add, remove, and modify elements as you go. Okay, so we know kind of what your robot is going to look like here. We've got our vertical cylinder, the cylinder that points into the screen. This object is made most clear by looking at it from a side view. So this object is going to have, the cylinder is going to have a radius of 0.1 and a length of 0.5. All of the cylinders in PyroSim are capped cylinders, so the ends of both cylinders have hemispheres attached to them. So that can be a little bit tricky. When we want to specify the position of the first object, we have to go up by 1 radius and up by half the length of the cylinder, which gives us 0.6 units of distance. Right? So there's our objects, our robot seen from the side, seen from the back. So there's the white cylinder and the red cylinder pointing into the screen. Here we're looking down onto our robot. So we can add things to this drawing depending on where it's most clear to add them. Okay, I'm sorry, so let me ask my question again. Where is the joint placed that connects the two objects?
0, 0, 1.1.
0, 0, 1.1, exactly, right? So we need to go up by 0.1 and up by the entire length, which is 1. So we're going to specify the x, y, and z of the joint, the position where the joint is, as 0, 0, 1.1. That's where we're going to connect the two objects together. Okay. So let's go back to the joints assignment here. Okay. So here's an example of continuing to annotate our picture here. So we've got our two cylinders. I've now drawn in blue the joint, and as I mentioned, the joint is not going to be drawn in the simulator, so we've got to keep track of where it is. These joints are going to allow the objects to rotate relative to one another. The question is, how should these two objects rotate relative to one another? Okay, so imagine that my upper arm and my lower arm are the two cylinders that I've attached together with the joint. I might want those two cylinders to rotate relative to one another through the horizontal plane. That's one option that I may want. But similarly, I may want the exact same two objects to also rotate relative to one another, but I want them to rotate through the vertical plane, right? So there's different planes through which the pair of objects can rotate relative to one another. So it's not enough to just specify the position of the joint. I'm going to have to give some additional information about how that joint is going to allow those objects to rotate relative to one another. How do we do that? Well, before we do, let's decide what we want these two objects to do. In this case, we're going to decide that we want the objects to rotate relative to one another through the YZ plane, right? So it's this one. We want these to rotate like this. So when we run our simulation, we're going to want to see the red cylinder rotate slowly down towards the vertical cylinder. Do you have a question?
Interact with each other?
Can they interact with each other? That's a good question. So PyroSim turns off collision detection and resolution between objects that are attached to one another. Actually, I misspoke. It turns it off between all pairs of objects. Because even when you don't create the joint, even when they're not attached together, the two cylinders interpenetrate one another. It's a good question. So in PyroSim, what it's looking for is collisions between cylinders and something else. What's the something else in our simulation so far?
The ground.
The ground, right? So the only pairs of objects that can collide at the moment is this object and this object, and this object and this object. These two objects do collide, they interpenetrate one another. PyroSim just ignores that collision and doesn't do anything about it. That's a good question. Yes?
Why is that?
Why is that? Because we're going to connect all of these cylinders together, and we don't want our robot to fly apart in a million pieces. Remember that PyroSim, when it detects pairs of objects that are not supposed to collide, it will apply forces that push those objects apart. When this cylinder comes to rest on the ground, there is gravity that's pulling down, so PyroSim is applying a force that's pulling that cylinder down. But the collision detection part of PyroSim is detecting the collision between these two objects and is applying a force pushing them apart, which in this case is pushing the cylinder up. So those two forces cancel out, and our cylinder stays stationary on the ground. Yeah? Okay, so we've got these two objects. We've specified the x, y, and z of the joint, and we want these two objects to rotate through the y-z plane. How are we going to tell PyroSim this?
Are we doing this via the rotation, or are we giving it a pair of vectors and then having it interpolate between the two?
Neither of those two options. Both of those options would work. There is a third option in this case, which is you're going to specify a normal vector. So you're going to specify a vector, again, in three-dimensional space. We call these N1, N2, and N3 just to remind you that this is the joint normal. If you remember from your high school geometry, a normal vector, or this vector, is normal to one and only one plane, right? There's a plane that's perpendicular or normal to this vector. Which plane is normal to this particular vector here? The YZ plane, right? So we're in essence specifying the plane through which we want the objects to rotate by specifying the vector that's normal to that plane. It's kind of weird. I guess we could have just done the plane itself, but that's how things are done. Yeah. So again, this can be sort of non-intuitive in our case, in your case, until you get started. If you need to think about where the joint should be placed. What plane do you want the pair of objects to rotate through? What is a vector? What is the vector that's normal to that plane? Pass that vector to PyroSim, and you'll get these two objects to rotate relative to one another, in this case, in the YZ plane. So what are the values of N1, N2, and N3 after all that build-up?
Negative 1, 0, 0.
-1, 0, 0, right? Exactly. That will give you that. It turns out, of course, that there are other vectors that are normal to this plane. What would be another one? -2, 0, 0, 1, 0, 0. Any of those will work fine. However, I want you all to use -1, 0, 0. And that's going to matter later because we're going to start to add motors to our joint, which is going to move the joint. And we're going to look at the angles that result as the two objects move relative to one another. If we all add -1, 0, 0, that means when the robot flexes or the two objects pull inward towards each other, that angle is going to be reported by PyroSim as a positive angle. So throughout this class, we're just going to pick an arbitrary convention, which is any part of the robot that flexes, pulls stuff in towards its body, those are going to be positive angles. And any extensions where it rotates parts of its body away from its center, those are going to be negative angles. It doesn't really matter one way or the other, but I want to make sure we all have the same convention. So we're all going to use -1, 0, 0. So far, so good? Yes?
Do you have the ability to lock the rotation after a certain angle? As in, like, I can't bend my arm past.
Absolutely, you can. So you can actually see on here, I don't think we specified in the assignment, there are two additional arguments that you can send when you create a joint, which is the low and the high stop, right? All angles in PyroSim, as you'll see in the joints assignment here, are in radians. So you give it a low stop, and I see there's an error in my drawing here. Low should actually be up here, and high should be down here. So the high stop, remember that contraction or flexing is supposed to be a positive number. So there's a maximum value inward that we might want to specify the objects rotate to, and a minimum angle outward that we want the joint to extend to. So I'll fix that after class, but low and high should be flipped. But I don't think you need to specify in this assignment anyways. Shouldn't matter. Yep?
Back to the whole clipping thing.
Yes.
Does it not recognize clipping with cylinders, or can you change it to where cylinders clip? Or would you
What
have
do you
to,
mean by clipping?
like so they can't clip through each other?
Oh,
or
so they can't
Collision.
interpenetrate.
If you
Collision.
wanted a
Okay.
collision, would you have to put a square on the rectangle so then when the cylinder hits the square?
Yes. So PyroSim hides all that from you, so you don't have control over that. But if you do want things that do not interpenetrate, add boxes. So you can replace some of the cylinders with boxes. Remember that a cylinder will respect collisions with anything that is a non-cylinder.
Okay.
Okay, so it's a little bit clunky, but again, it's easier than getting into the nitty-gritty details of collision detection and resolution. Pairs of cylinders will always interpenetrate one another. Any other questions? Okay, I think those are the most non-intuitive aspects of assignment 2 and 3, so I'll leave it there for now. Let's see. So you will probably notice that in the last few days I've added some more. Oh, sorry, you had a question.
Is it okay we send our image with code?
It is okay if you send your image with code. That's a good question. I would prefer that you don't. The whole idea behind this class is you're only submitting the output of your code. The reason why is if you submit it with your code, it's on Reddit, anyone else can see your code, and we want people to build up an intuition for developing their own code. If you're stuck, come see us in office hours and we can do things that way. If I saw that some of you did submit an image along with code, that's fine for the first assignment, but I just ask in subsequent submissions, just images or video, not a snapshot of your code as well. Thank you. Okay, so again, you'll notice that I put up a few new assignments. I'm keeping 1 week ahead of the grad students, so there's 3 waves of us going through this progression. I'm trying to keep out in front here. The grad students are nipping at my heels, and the undergraduates are coming along one assignment at a week. If you do finish an assignment early and you want to move on to the next one, that's perfectly fine. You're welcome to work ahead if you want to. Okay. Any other questions about the assignments before we get back to lecture? Yes?
Can I ask a question about the sensors?
About the sensors project. Yep.
In the requirements that it says that I need to submit for a 4 screenshot, and so do you mean that those 4 screenshots are the plots about drawing from the data, or just a screenshot of the data itself?
A screenshot of the data itself. So you're asked to create at least 4 plots of the sensor data in this assignment. That's what we're asking for. Yep. Okay. I'll put in some language to clarify that. Yes?
What is the significance of the little pyramids on the ground? Is that just for orientation?
That's just for orientation. That's just for you to get a sense of whether you've got things in the right position and the right proportion and so on. Yep. Any other questions? Yes?
So for the rotation part,
Yep.
we can only rotate in one direction. Can we add another normal vector which allows it to rotate in different directions?
That's a very good question. So the question is, can you only specify a joint that causes objects to rotate through the plane, right? So obviously not all our joints work like that. Your shoulder joint allows much more rotation of your arm relative to your torso than your elbow does upper arm to lower arm. Open Dynamics Engine is the actual physics engine that's being used under the hood in PyroSim. Open Dynamics Engine, or ODE, allows lots of different kinds of joints, and for the moment I'm suppressing those. If you do want to create a joint that allows more degrees of freedom, put 2 hinge joints together for the moment. So it's a bit of a hack, but imagine that we have 1 capped cylinder like this, we have a second capped cylinder like this, we then have a third capped cylinder here. What's the length of this third capped cylinder that I've just added? 0, right? So it's got the same radius as these 2 objects, but it's got 0 length. So if you run this, you shouldn't see anything other than 2 cylinders, right? So we've hidden a third cylinder inside the intersection between cylinder 1, cylinder 2, and cylinder 3. Right? I can then create a joint that attaches C1 to C3, and I can place the joint there. And I might give it a normal that points towards us into the screen. I then create a second joint at the same position that connects C3 to C2 and give that a different joint normal. And now I have these two joints which allow, I guess I'll have to do it with my shoulder joint here, right? So it allows this motion and this motion. So in essence, this object can move this way relative to this object. Right? Okay, as we move onward through the assignments, I'll add some more joints that are possible, like a linear joint or a linear actuator, which will allow two objects to lengthen relative to one another or compress inwards towards each other like a piston. They're not in there yet, but they're coming. But for the moment, if you want to play around with this, you can do it by aggregating together hinge joints with different joint normals. Okay. Any other questions before we move on? Okay. So let's get back to lecture. I'm sorry, before I do, some of you attended my office hours on Twitch yesterday. If you want to go and watch that, I taped the office hours and they're up on YouTube now, so you can go and watch that as well. Okay, so we're working our way through kind of a very brief history of AI and robotics, and we're sort of just looking at all the different approaches that have been attempted to try and understand or create intelligent machines. A lot of this history is very philosophical. People have very different opinions about it. I have no expectation that you will form a particular philosophy about any one approach. I'm just trying to give you a feel for what's out there. Okay, so I think we ended last time in the 1980s with Valentino Breitenberg, who was trying to make the point that we can often get relatively, well, maybe useful behavior. I don't know about interesting. We can get things like phototaxis, driving towards a light source, or photophobia, running away from a light source, with very, very simple circuits, as long as we think about the body and the brain of our vehicle, or our robot in this case, right? So we need to have two sensors, one front left and one front right, two wheels at the back, and with just two wires, we can get either photophobia, or if we cross those wires, we can get phototaxis, right? So very, very simple brain, but again, from the starting point, Breitenberg is already thinking carefully about the body of the robot as well. This is pretty important. Okay. We'll see why a little bit later today. Okay, so let's see. So we're in the 1980s now. We talked about Eliza last time. Eliza was this chatbot that sort of took input, broke that sentence down into its component parts, moved those parts around, and so on. There are a lot of these rule-based approaches to AI from the 50s all the way up to the 80s. And in the 80s, there was this revolution to say, wait a second. Biological nervous systems, it's not clear what they do, but they certainly are very distributed, right? We have lots of different senses that are, we have a lot of information that's arriving along our different senses. Whatever the brain does, it's a massively parallel system. It's unlike our traditional computers back in the 80s, which were not parallel. They did one thing, right? They took in a sentence, broke it into pieces, rearranged those pieces, and sent them back out again. So starting in the 1980s, there started to appear these artificial neural networks. We're going to see quite a bit about that in this course here. So an artificial neural network was a model of biological neural networks, or nervous systems, and they shared some properties in common with biological nervous systems. The main property was that they were more or less arranged in layers. At the top layer, or the sensor layer, information from the outside world arrives at these neurons. So these circles are meant to represent neurons. The sensor values arriving here are passed from one neuron to another along what Breitenberg would call a wire, but we're going to start calling now synapses, right? Connections between neurons. And in a complex neural network, like this one, you have lots of interconnections between neurons, and all those interconnections, for our purposes for the moment, is just a transformation of a vector of values. So if you think of all the values that are arriving here as a vector, it's transforming them into a new vector. If we take our artificial neural network that's made up of in this cartoon example here, 4 neurons and 2 synapses, and we drop it into a robot. And the sensors of the robot supply values to the first layer of neurons, and the values that arrive at the last layer, those are passed on to the motors, which drive the joints. You're going to see that in assignment 4. You start to drive the motors, we get a robot that moves in response to sensory information, right? This little cartoon neural network is really not that different from a Bradenberg vehicle, right? We have 2 sensor neurons here and 2 motor neurons here. They have 2 wires, and away we go, right? So in robotics, an artificial neural network transforms sensory signals into motor signals. Okay. We might also just consider an artificial neural network on its own, where we're supplying the input and we are interpreting the output somehow, right? So we sort of thrown away the body of the robot and we're just looking at artificial neural networks on their own. So this was a very powerful idea that emerged in the 1980s. It had some fundamental problems and sort of went out of fashion very quickly and plunged the field of robotics and AI into what's now become known as the AI winter. So there was this promise in the 80s that suddenly we had everything worked out. We were going to make intelligent machines using these things called artificial neural networks. They weren't quite working well. No one could figure out why. So in the 90s and the zeros, they sort of disappeared from view until 2006 when they came back with a vengeance. And now all of the hype about AI basically is coming from this new rebranding of artificial neural networks. Now they're known as deep learning or deep networks. You can see why they're called deep networks because they have lots and lots of layers in between their input layer and their output layer. So the fundamental problem with artificial neural networks back in the 1980s was that we could get neural networks to do simple things with just 2 or maybe 3 layers, but no more. If we don't have more layers, there's only certain kinds of transformations we can achieve between input and output. These are relatively simple transformations. Now, there are some innovations in the field, and we're not going to go into those innovations in this class here, but those innovations now allow investigators to train deep neural networks with many, many more layers, and they can perform many, many more transformations. Why does that matter? Why do we want a neural network to perform lots of different transformations? Well, there was an observation from biology that the mammalian brain was organized in these layers, especially in the visual system. So imagine for a moment that all of these input neurons here are the rods and cones in the eye of a mammal. And there's very little information arriving at any one individual rod or cone. But you can see that the neuron 1 layer upstream is combining information from this rod and cone and some neighboring cones. So this neuron is kind of looking at a few neurons downstream, meaning towards the retina, and combining that information in some way. And these connections have particular weights or influences so that these neurons influence this neuron in a particular way. And depending on the pattern that arrives at this small subset, if that pattern is just right, it will cause this neuron to light up. So, for example, what you start to see in a lot of deep learners, if you train them on images, so we take our retina here, if you like, and in this cartoon example here, it's just a one-dimensional line, but imagine it's a 2D vector of pixel values. We take an image and we place it on the input layer here. We start to see that when this network is being trained or optimized, and I'm not going to go into the details of how this is done, but we start to train this network to, for example, recognize faces, we will see that at the first layer up the hierarchy, these neurons start to light up. Well, let's take this one here. This one starts to light up when a small patch of the vector array has a diagonal line in it. And this one will light up when there's a horizontal line in a slightly different patch. So you start to get, as you move up the hierarchy here, you get neurons which are looking, quote unquote, at a bigger patch of the original image, and they will light up when they see more and more specific patterns. So these are turning on and off depending on just the grayscale value of their single pixel that they're responsible for. This one looks at a bigger patch and only lights up when there are these sort of diagonal lines. If we go further up, we start to see neurons that can sort of see downstream. They can see the whole pixel array, and they will only light up when there's a face. This neuron over here will only light up when there's a cat. So in essence, what's happening is we have raw pixel values coming at the input layer here, and these pixels will start to report if they see the thing that they're supposed to see. The guys down here near the bottom say, I see a horizontal line here. This guy says, I see a vertical line over here. This guy up here is looking at the horizontal and vertical lines and patches of color and so on and says, aha, there's a dark patch here, a dark patch here, a dark patch here, a dark patch here, light patches here, darkness all around. That's a face. I light up. Right? Okay. So again, I'm not going to get into how these are trained, but there were some innovations made to actually make this process work. So now we have deep networks where you can hold up your camera and it immediately identifies the faces, right? Draws that little box around the faces in your camera. That's usually what's going on in most cameras these days. That's the deep learning revolution. There's some interesting things you can do with deep learners. So usually we supply a photograph or a YouTube video at the input layer here, and at the output layer up near the top, it will say there's a face in this image or video, or there's a cute kitten in this video, or whatever. You can also turn things around. You can take an image of a face, an actual face, or I'm sorry, I take that back. We can instead take one of these upper level neurons and stimulate it. So we can artificially apply a high value and suppress all the others. And that value will now start to flow down to the input layer. What do you think you would see at the input layer?
To produce some kind of face?
It produces some kind of face, right? So you're in essence telling this deep network, think, quote unquote, think about faces, and a face will appear down here. So if you Google deep learning hallucinations, you can see a whole bunch of these things in action. They're kind of a lot of fun. Okay, so that is the reason, that's the main reason why robotics and AI has come back into fashion with such a vengeance. There's been some innovation in the field around what used to be called artificial neural networks and are now called deep networks or deep learning. Okay, so I mentioned this idea of the AI winter already. AI research tends to wax and wane because hopefully, as you realize by now, creating intelligent machines is an incredibly difficult thing to do. Decades can go by where there's little to no progress, and then suddenly there's an advance and there's a lot of excitement. Intelligent machines are just around the corner, and at least so far that promise has not really occurred. So back in the 1950s at Dartmouth, remember that the founding fathers of AI promised that they would make intelligent machines during the summer of 1956. By the 1970s, everybody was still waiting, so we had the first AI winter. All the hype in 1956 was never realized, went out of fashion. 1980s, this idea of artificial neural networks was proposed. Everyone got very excited that these ANNs in the 80s were going to give us intelligent machines. That never panned out. So we had the biggest winter in the 1990s. Things have been kind of quiet until the last few years. Now we're enjoying an AI high summer. So everybody in the field is asking, how long is summer going to last? We'll see. We'll see. Right? Okay, it's an interesting time to be working in AI. Hans Moravec was a very famous roboticist back in the 1980s, and he wrote an interesting paper about why these winters tend to occur. DARPA is the research wing of the American military, so many researchers in the 70s were caught up in a web of increasing exaggeration. They were making these promises to DARPA that had been too optimistic, so they're making promises because obviously they wanted funding. Unfortunately, what they delivered stopped considerably short of what they had promised, but the next time they wrote a research proposal to DARPA asking for money, they couldn't promise less than what they promised the time before, so what did? they promise more, right? So there's a lot of politics going on under the hood of all of this AI research, and so there you go. We'll see what happens. Okay. Okay, so we're about to finish lecture 2 here. Again, this was not a very deep history of AI. I've just tried to touch on a lot of the different approaches for you. And now stepping back from all of the things we've talked about, there is a basic structure you can see to all the different attempts to create intelligent machines, and they sort of fall into these 2 different branches. One branch over here is artificial intelligence, and then we have all the different robotics approaches over here, and obviously in this course we're going to be focusing on one particular branch in robotics. What is it that distinguishes AI from robotics? If you had to give a summary of what breaks this tree into 2 branches, what is it?
It's a little crude, but like robotics is the physical robots adapting physically to their environment, like setting something on Mars and having a rover adapt to the harsh environment on Mars. And artificial intelligence is more similar to a chatbot, where it can learn from the environment around it and react in a more intellectual way.
Absolutely, right? So summarizing even further, every approach over here is trying to create intelligent machines that don't have a body, right? And all of the approaches over here are also trying to create intelligent machines, but machines that have a body. You remember that we started this lecture in the 1600s with René Descartes. René said, I know about the soul, I know about myself, the body and the external world, I'm not so sure about, let's throw that part away. That part's not so important, I don't know about that part, this part I know about. Looks kind of familiar, right? So there are a lot of AI researchers that say, humans are intelligent, yes, we have a body, but that's not so important. All that matters is what's happening on the inside of the skull. Everything else we can throw away and just focus on trying to create intelligent, non-embodied machines. That's the curse of Cartesian dualism. It plagues a lot of my colleagues. As you can probably imagine, I belong to this camp over here, where roboticists tend to believe if we are eventually going to create intelligent machines, they're going to be machines that have a body. They have bodies with which they can push against the world, literally or figuratively, with their own bodies, and observe how the world pushes back. There's a sensory repercussion of action, and it's that feedback loop. I push against the world and see how the world pushes back. That feedback loop is going to be the raw material on which all intelligence is built. So, again, you know which camp I belong to. I don't expect in this class that you choose any one particular camp, but we're going to spend most of the rest of this course talking about evolutionary robotics. So, in the next lecture, lecture 3, we're going to focus now on just the right branch of this, and we're going to talk about embodied cognition. So if we want to understand cognition or intelligence, we're going to try and understand it in an embodied context. So throughout the rest of this course, I'm going to talk about embodied and non-embodied approaches to intelligence. You now should see where that divide comes from historically. So far, so good? Any questions about lecture 2? Okay, so let's move on now to embodied approaches to intelligence. And the way we're going to do this is we're going to take some of the building blocks of intelligence, right? As we talked about last time, intelligence, if you actually sit down and try and write a definition of what intelligence is, it's exceedingly difficult. What's a little bit easier is to say, well, okay, something that's intelligent must be able to do X, Y, and Z. And if that machine or that organism is missing X, Y, and Z, we probably wouldn't think of it as being very intelligent. Right? So what's one important building block of intelligence? Well, recognizing patterns. We just talked about deep learners, which are now pretty good at recognizing patterns. And they do so in a particular way known as image segmentation, or that's the name for it in computer vision. So I give you a picture of this person. Who is this person? You still know who that is? Okay, good, right. So we've got Marilyn Monroe here, and you immediately see the person in the image, right? Hopefully, for most of you, it took a hundredth of a second to recognize, first of all, that there is a person in this image and who it was, right? It's trivial for you to do. people started on this problem, image segmentation, back in the 60s, not quite at the beginning, but in the 60s. And this didn't work very well for 50 years until deep learning came along, right? It was an exceedingly difficult problem, right? I should change the slide now. It was one of the most difficult problems in computer science, right? So there's lots of reasons why this problem is difficult. One of the reasons why is because most of the approaches to solving this problem have been using the non-embodied approach. We take a computer program that has no body, we supply it at its input layer with an image of Marilyn Monroe, and we train it to produce at the output a signal that says, yes, there's a human in this photograph, or no, there isn't a human in this photograph. We have, in some sense, crippled the machine because we don't work that way. Or do we? How do you recognize Marilyn Monroe? You all have bodies, but you're not really using them to recognize Marilyn Monroe, right? I just put up the slide and some light patterns fell on your retina and you recognize Marilyn Monroe, hopefully.
It doesn't really matter about my body, but I know she's a humanoid and I see other humanoids.
Perhaps,
2
right?
limbs, 2 legs.
Yes, that's right. So there's something about the fact that she also has a body. Yes. But I could also put up a non-human object and you'd probably recognize that. So this is a little bit tricky. So let's step back from this problem for a moment. So the deep learner that I showed you is the non-embodied approach to pattern recognition. Let's take the same building block of intelligence and now approach it from an embodied point of view, right? So now you can obviously see who the learner is in this case. This is some work on the COG robot at MIT carried out by Georgia Mehta and Paul Fitzpatrick over a decade ago. So what they did is they had this robot, and again, this is a cartoon of the robot, but it highlights the most important parts of this robot. The robot has 2 cameras, so it's got 2 eyes, and 1 arm that it can move more or less like this. That's it. Okay. The signals or the video streams that are arriving at the 2 cameras are stripped down in a very interesting way. They threw away all the color information, and what they did was they took each pixel in those 2 images, and they labeled the image as either moving or non-moving. So we've tried to represent this in this cartoon here. So they take those 2 images, they put them over one another, and there's a little computer vision algorithm that goes through these combined images and determines whether the pixel registers movement or not. So in essence, they're taking not just the current pair of images, but the one from the time step before. And if the brightness of the pixel changes from time step t-1 to t, that's motion. If there was no change in brightness at that pixel, no motion. So you can see this in the cartoon here. Everything that's kind of grayed out, those are parts of the robot's visual field in which it's detected no motion in the last few milliseconds. The arm that you see here, these are pixels that are reporting motion. So we've actually drawn the arm in there, but you can imagine that the robot just sees patches of gray and black. Gray means no motion, black means motion. Okay, that's it. That's all the robot gets for now. You can see that they've placed some fruit in front of the robot. The robot doesn't know much about its world at all yet. What it does know is that it can send signals to its motors. So it sends some signals to its motors, and its arm starts to do this. Our robot suddenly sees, first of all, it sees a field of all gray, and suddenly, when it sends signals to the motors, it sees this blob of black enter from the left side of its visual field. What can this robot infer about that black blob?
It is moving.
It is moving. How does it know it's it? Maybe it's something else.
It knows that the black moving into its visual field was correlated with its motors activation.
Exactly, right? So the blob appeared the moment that it started moving its arm, right? Cog might then decide to just stop sending signals to its motors. At the beginning, it's just kind of random. And the minute it stops sending signals to its motor, its arm is still in front of it, but its arm has stopped moving. What happens in its visual field?
Great.
Everything goes gray, right? The blob suddenly disappears. It moves again, the blob appears, it stops moving, the blob disappears, right? So you'll notice that already in Cog's world, there is a relationship between action and sensory repercussion. The blob shows up, the blob disappears, right? We already have this basic feedback loop between the robot pushing against the world and seeing how the world pushes back. In this case, the world is its arm, right? So BabyBot says to itself, okay, I don't know what that blob is, but that's me, right? Kind of like Descartes, right? I don't know about anything else, but I know there's this blob and I can get it to appear and disappear. It's me. It's under my control. Okay, so BabyBot is Cog is playing around. There's a similar robot called BabyBot. I always get them confused. This is Cog. Cog is moving its arm around and the black blob is there. And then suddenly, the black blob changes shape. It suddenly gets much bigger. What is Cog supposed to make of this situation?
Something was added to him.
Something was added to him, right? So is this new part of the blob, so if it subtracts the me part of the blob and just has this remaining piece, what can it say about that piece? It exists in the environment, right? So maybe Cog hit the apple with a fair bit of force and then stopped moving, so this blob disappeared. What happens to the apple? It's still moving, right? Which means BabyBot still sees it. So this is something different. Cog has not realized that yet, right? So now there's something in its environment that moves even when it stops moving, right? So Cog says, okay, this is me, and that thing over there is the world, right? There's already a difference between self and non-self. This is also an important part of intelligence, which is still kind of mysterious about how babies do this. When babies are born, they don't even know this distinction between self and non-self, right? How do you actually decide or learn where you end and the world begins, right? So BabyBot is actually playing this self-non-self discrimination game. And by doing so, it gets something for free, which is image segmentation, right? It knows exactly the shape of this thing, which it says, well, for lack of a better word, I'm going to call that thing apple. So it knows the shape of this thing, because when it moves, it automatically sees the shape. You didn't push against Marilyn Monroe, so you didn't have that advantage, right? What else can BabyBot tell about this thing it's decided to call an apple?
Would it assume that it changes shape? Like when he hits it with his hand and the apple's behind his hand and rolls, the apple to himself is growing.
Possibly.
As opposed to just moving.
Right? So BabyBot may see that this object can change shape, right? Maybe there's this occlusion thing that happens, possibly. Most of the time, it's going to notice that this thing doesn't change shape, right? It pokes this thing and it rolls a little bit, maintains shape, pokes it again, maintains shape. What else can BabyBot infer? What other properties of this thing called an apple can BabyBot infer? Does this thing always maintain the same position, right? We just were talking about objects. Objects have position, shape, orientation.
Maybe mass properties based on motion.
Maybe, right? So BabyBot sort of knows how much force it's applying. And even with just a little bit of force, this object moves its position a little bit, right? Let's say it's playing around and it happens to push the banana. What happens now? The minute it comes into contact with the banana, what new things does Cog learn about the world?
Not all things roll.
Not all things roll. What else does it learn? So suddenly now there's something that takes maybe some more force to get it to change position. So maybe it says, all right, there's this new property, and I'm going to call this property mass. And that thing called Apple has less of it than that thing. What else can BabyBot infer? Yep.
Shape, different shape.
Different shape, right? So suddenly there are these things that have different shapes and are moving differently. So there's things that have different shapes, things that have different mass.
About the whole baby thing. I know when you're a toddler, if you don't see it, it takes a while to recognize that things you don't see exist.
True.
And would this have that issue of the apple stopped moving and it's no longer there? Does it still exist?
Not according to Cog, right? It's gone. So of course, this is a very simple robot, and there's only so much it can learn about its environment. Okay. What else can BabyBot learn here? So maybe BabyBot is waving its hand around and side to side and up and down, and it takes its hand and does this on the grapes. What happens? Squishes them, right? So what does BabyBot, what does Cog see in this case? Juice. The shape changes, right? It deformed the shape, and when it takes its hand away, well, it stops moving. I guess it can't see it anymore, but the shape doesn't magically go back again, right? So there's certain effects Cog can have on the world that aren't easily reversible, right? A very important lesson on the road to intelligence.
So is that a quality of elasticity?
It could be, right? Well, it's a property. It's a property of lots of things, right? So it's a function of lots of different physical properties. What I want you to take away from the Cog example here is, by the very fact that Cog has a body, it can learn lots of things about its environment by action, right? And one of the things it happens to learn is shape, right? So if we put enough objects in front of Cog, it would start to learn that things that are round, let's imagine that it came up with the word round for things that have this shape, they also tend to be things that require relatively little force to get them to move. So things are round and also rollable. So now we're introducing an adverb into Cog's world, right? There are things that there are properties of actions, right? This thing is rollable, and it has to do with its shape. So it's learning lots of things about its world around it, right? If we were to take off this filter from Cog's vision and allow it to still see things when they stop moving, we could keep playing this game, and hopefully Cog would be able to learn to recognize apples and bananas and animals and humans without having to physically interact with them. But there is an interesting theory in developmental psychology. Developmental psychology is the study of development, or how infants develop into humans, that it's these actions, these interactions with the world that provide the raw material that allow infants and then toddlers and then adults to gradually be able to recognize and infer properties of external objects without having to interact with them. Okay, we'll come back to that later in the course, but again, just to show you that in some cases we can make some of the challenges of intelligence, like recognizing objects, easier if we give the machine a body with which to interact with the environment. This is a very difficult problem. It's now a solved problem, but it took 50 years to do so for a machine that does not have a body. It has no experience of interacting with the world. So that's the non-embodied and embodied approach to pattern recognition. Let's take another building block of intelligence. So an organism or a machine that can't plan into the future, you would probably say that machine or that animal is not that intelligent, right? One building block of intelligence is being able to think and plan ahead. Okay, so planning, this is a task that has been studied since the 1950s. Planning is very important in formal games like chess. So a very pivotal moment in AI was when Deep Blue beat Garry Kasparov, that time the world champion in chess. Anybody remember when this was? Very good. So Deep Blue won its first match against Gary back in 1997 and won its first game back in 1996. Okay, so Deep Blue is again a non-embodied machine. It did have a huge mainframe. It had a physical body, but it didn't use it to learn about chess. How does Deep Blue work? How did Deep Blue work? Anybody know?
Try to think of the possible moves and then which move would get to the best possible outcome.
Absolutely, right? So this is known as a min-max tree, right? So there's the current state of the board, which is the root of the tree. I consider all the moves I might make right now, which becomes the next level in the tree. And for each of those possible moves I might make, what are the possible moves that Gary might make in response? And this tree branches all the way down, and I'm now going to try and decide which branch of the tree to follow, and the branch of the tree that I'm going to follow is the one that has the most number of leaves, or end game, in which I win the game and Gary loses, right? Got much more sophisticated than that, but at heart, that's more or less what's going on. So the early approaches to getting machines to plan was to build these trees where the machine would think, I do this, and then humans or the world does this, then I do this in response, and so on and so forth. And my programmer wanted me to reach this desired state, so I'm going to perform this action and move the tree towards that set of outcomes. Okay. Okay, let me skip ahead for a moment. Let me skip ahead to the embodied approach to planning. This is Shaky the robot, another very famous turning point in the field of AI. Shaky was built at Stanford in the late 60s and the early 70s, and Shaky was designed to try and deal with this planning problem. So here's Shaky. This was pretty amazing in the 1960s because if you look carefully, there are no wires snaking out of the photograph. All of the computers controlling Shaky were on board, which was amazing at the time. Why do you think Shaky was called Shaky?
It shakes.
It shakes, absolutely. So Shaky was placed in a lab, and you can see they would put some objects around it, and they would tell Shaky, Shaky, get to the door, get out of the lab. So Shaky would sit there, scan its environment, create a model of its environment. So again, this is not the actual model that Shaky made. This is one from one of my own projects, but just to sort of give you a feel for what was going on inside the onboard computers of Shaky. It would make a model of its environment. It would then plan, given the model, it would plan a route that would allow it to get to the door by avoiding the obstacles. It would turn and make one move, about 1 inch of travel, and it would shake while it was doing so and then shake to a standstill. Then what would it do?
Turn and shake somewhere else.
Turn and shake again, right? But before it moved again, it would have to remodel its world because it's moved, and now it realizes that something that it thought was an obstacle is actually a shadow. So that might open up new possibilities, or something it thought was a shadow is actually an obstacle. It has to sense, model, plan, and move all over again, right? Okay, so in 6 minutes' time, when class finishes, is this what you're doing? Hopefully not, right? It'll take you a day to get out of the room. Now, in all fairness to Shaky, Shaky was using 1960s computer technology. But even at the time, people started to realize this is probably not a good way to approach intelligence. Move, stop, sense, model, use that model to plan what you're going to do next, carry out some part of that action, stop, sense, model, plan, move again, and again, and again, and again. Why not?
It's not intelligent.
Well, it's not intelligent. Why not? What's the problem here? Shaky would get out of the room after about 2.5 days. Again, 60s technology. If you did it today, it would probably take Shaky maybe 8 hours. Much faster. What's the problem here?
It's too slow.
It's too slow, but why is it too slow? There's a fundamental assumption Remember, we're still in the history of AI and robotics here. There's a fundamental flawed assumption here.
Is it because it's throwing out all the data it got the previous model?
It throws out a lot, right? Not all of it, but yes, some. It's got a sort of, there is a lot of redundancy here, but that's not the real problem.
Well, it throws it out for lack of the ability to differentiate between things.
Yes, so its sensing is not perfect. Ours isn't either. What's the fundamental assumption here?
Is it that it doesn't learn?
Learning is missing here, but that's also not the problem. So remember, Shaky here was created in the 60s. It took sort of until the early 80s for people to start to realize the fundamental flaw here. It's very sequential, right? Does this machine, or do we have to do all of these things one after the other? Right? Remember, the brain is incredibly parallel.
Is it because when you're sampling like your environment, you're just doing it in the most efficient way possible for whatever the task is? So it's just not being, it's not like taking the sample that would make the most sense to get out.
It could, right? So here we're sort of, again, not being fair to Shaky and assuming that Shaky is kind of modeling a lot of its environment. Probably doesn't have to model the entire room, just some subset of it. Yes?
Is it that after it moves, technically the model or the environment changes?
Right. After it moves, the model, it's going to have to update at least some part of the model, right? This is tricky. So there was a revolution, a different revolution in the 1980s that was led by Rod Brooks, who later became the director of the AI lab at MIT. Rod said, all this modeling and sensing and acting, it's all sequential. Let's throw all that stuff away and get back to parallelism. Right? So it was known, obviously, in the 80s and much earlier that whatever it is the brain does it in parallel. Right? It isn't this sort of sequential, do all these different things one after the other. Let's try and parallelize the way that a robot gets around in its environment. And so Professor Brooks proposed a particular architecture, a cognitive architecture, a way of building a brain for robots. This is not an artificial neural network. This is known as subsumption architecture. So who has a Roomba at home? A couple people have a Roomba? Okay. So after leading the AI lab at MIT, Brooks went off and founded iRobot Corporation, and one of their products is Roomba. If you break open your Roomba and analyze the circuits, this is what you'll find inside, subsumption architecture. Okay. Here's how it goes. So Brooks had already kind of had this idea back in the 80s. You will see that the particular behaviors of this hypothetical robot are not that different from Roomba. Okay. What's one of the most important things a robot should do as it's moving around its environment? It shouldn't smash into objects out there. So that's the most important thing that a robot should do. So it's got some sensors that allow it to detect obstacles. Doesn't really matter for our purposes what those sensors are. It takes that sensory input. It tries to figure out whether there is an obstacle and then sends commands to the motors so that if there is an obstacle that's close on the left, it turns away from that object. And if there's an obstacle that's close on the right, it turns to the left. This should sound familiar. We've already seen a hypothetical robot like this. What was it?
Brainbird vehicle.
The Brainbird vehicles, right? Really, really simple. So this circuitry, not very difficult to put in there, right? But we'd like our robot to do something other than just drive around and avoid obstacles. So let's assume that we also want it to avoid loud noises. So perhaps there is a 6-pound furry organism that happens to exist in the home, and this organism happens to change shape, so it's difficult to determine that this cat is an obstacle. So the obstacle sensors are not very good at that. However, this organism happens to hiss whenever the robot gets close to it, so the robot is also programmed to avoid loud noises. So it avoids loud noises as it's moving around. But if at any point while it's moving around and kind of moving away from sound sources, if while it's moving away from a sound source, it happens to get close to an obstacle, avoiding obstacles is more important than avoiding loud sounds. This is more dangerous than this situation. So if this
part of the architecture ever lights up, saying there's an obstacle nearby, it subsumes control of the motors. It takes over control of the motors, and it takes that control away from this component, which had picked up on a sound and was directing the motors to move away from a sound. So the intuition behind the subsumption architecture is you can do sort of higher order things, but if any of your lower level needs ever put up their hand, those should be responded to immediately. So in the Roomba, or any robot that has a subsumption architecture, there are all these different components of the robot's brain that are doing some computation. Is there an obstacle nearby? Is there sound nearby? Is there a light source nearby? They're all computing what they do in parallel. And as long as the lower ones are quiet, meaning they say, I don't detect the thing I'm supposed to detect, then the higher order things are allowed to control the motors. But if any of the lower things in parallel ever light up, they immediately take control of the sensors, right? So very different from shaky. We're back to a parallel organization now, where the robot is thinking about different things in parallel, but any one of those things can take over control of the robot at any time. Okay, we're out of time for today. Reminders, you have a quiz due tonight. And undergrads, please get started on assignment 2. Grad students, please move on to assignments 3 and 4. We'll see you on Thursday.